Okay, so this is what we looked at. I wanted to just go ahead and talk a little bit about what to do if you want to get T-star values without using a table, right? Because it might be that the T-star number that you want isn't on your table. So we can just go ahead and rely on the calculator using inverse T. So for number 1 here, and this is in your packet, I think it's a few pages in, what is the critical value that satisfies the condition that the T distribution with 15 degrees of freedom has a probability of 0.9 to the left of T star? All right, so let's go ahead and illustrate this with a curve and just make a bell curve because T curves are bell curves. And if it's 0.9 to the left of T star, and that makes that 0.9 on this side, which leaves us 0.1 to the right of it, and that cut point is where our upper tail T critical value is. So in order to go from a proportion or a probability to a Z or a T, well in this case a T value, we need an inverse T. So inverse T, and it takes 2 criteria. You need the left tail from negative infinity up to where the cut point is. You need that probability, so that'll be 0.9, and then just the degrees of freedom so that the calculator kind of knows what curve to be in. All right, so let's go ahead and roll over to the calculator, and a calculator page in the scratch pad is fine. So it'll be menu, and remember it's under probability. It's the same place where normal CDF inverse norm is. So probability distributions, and voila, inverse T. Area we know to be 0.9, and degrees of freedom were 15. Can't get any harder than that, so hit OK. So 1.341, 1.341. Now if you want, you can pause this and do number 2 on your own. I'm just going to go ahead and do it. I did let the kids do it on their own, and it was like pretty much doable, but now we're going to have a critical value that satisfies the condition that the T distribution with 24 degrees of freedom has a probability of 0.15 to the right. All right, so the smaller value is to the right of your cut point, so that would be your 0.15 here. That would make the rest of this 0.85, right? And since you're going from left to right, when you set up your inverse T, that's the number you need, the 0.85. So it's just inverse. Oh, yeah, this is to figure out this T star value. So inverse T, and that will be 0.85 for the left tail probability. And we had 24 degrees of freedom. So in the calculator, we can probably just go up and paste from here. It might save maybe a few keystrokes, I don't know. So 0.85, comma's down below pi, and 24, and just go ahead and 1.059. That's it. Easy peasy. Okay, so what I wanted to do to kind of finish this up is show you one more feature of your TStarZStar table, which is a little bit out of date, and you probably will never use it, but it's good to know what the entire thing is. Let's just teleport back to circa 1960, and remember, no computers, no calculators, no fancy Nspires. Maybe there was a calculator out there, but it was super expensive, and so you're doing stuff by hand. And let's just say you're doing a test of significance where n is 17, so that would be 16 degrees of freedom. And let's say you're calculating t value, and that's just the formula for it is x bar minus mu naught from HO over S adjusted by square root of n. And let's just say that you do all of this and plug in the numbers and you get a t-value equal to 2.953. All right? So that's what you need a p-value for. Well, how are we going to do that if we don't have technology? Well, it's just like anything else from back in the day. We're going to use that TStarZStar table, much like people use log tables and trig tables and all different actuarial tables, just all different kinds of things. Okay? So let me go ahead and pause this for a moment, and I want to open up the table in just a second. All right, so here we are back, and this is one of those tables, and what we're used to is pretty much working down here for getting t-star values for confidence intervals, so we would pick whatever we wanted, say 95% confident, and if it was, proportions, we just read up because that would be in a Z. Otherwise, we would go up and down here and pick our degrees of freedom. By the way, if you get up to like 30 or 40, you can probably pick whichever of these t-star values you want because you're going to get pretty much the same thing. But anyway, that's what we used it for. But now remember, we're doing a test of significance and we had a t-value of 2.953. And we're trying to get a p-value. We can use this table to help us out, believe it or not. Now something like 2.953, and leave it to me to put that wrong number there. So let me just fix that, because let's get this fixed up. And we can use this to get a p-value from, believe it or not. Having this exact value for t-test statistic would be highly unlikely. There are a lot of numbers in here, but there's certainly not every single number there is. So we're just going to have to do a little bit of estimating. So if we scroll up here, these are p-values. They're a single tail p-value. They're basically for a right tail, but we could do left tails. We get negative, and we can just drop the negative from it. All right. So we had 16 degrees of freedom. That puts us right here. And we're just going to go over and over and over. Remember, it was 2.953. We're just going to highlight those numbers to either side. All right? So there they are. 2.921, 3.252. And if you go up, you can isolate that on one side of your t, and you can isolate this on the other side. And somewhere in here is your p-value, right? So what do you do? All right, you've got a p-value 0.005 on the one side, and you have a p-value equal to 0.0025. Well, just consider if you have an alpha of 0.1. You would reject, right? Because yours is somewhere in between here, and that's less than what your cut point is. Let's say you have alpha 0.05. You would still reject. Alpha of 0.01. Both of these are below that, so you would reject. You would need an alpha that would be way, way out there in order for you to fail to reject. All right, and these are pretty much the usual ones. So here we would have p, we'd say something like, since p is between 0.005 and 0.0025, the results are significant, and we would reject HO. So we can make a decision even though we don't know what the exact p-value is, because we know where it is between what two numbers, and that's enough.